Hi everyone, today we're going to be doing a proof by induction, and the statement that we're going to be proving today is that n factorial is greater than 2 to the n for all natural numbers greater than or equal to 4. So the first step that we take in any inductive proof is to start off with our base case. And in this case, our base case is going to be when n equals 4. So we say, let n equal 4. Then if we plug in 4 into this, we get 4 factorial is equal to 24, and 2 to the 4th power is equal to 16. 24 is greater than 16, so the statement holds when n is equal to 4. We'll notice that we start with 4 and not maybe 1 as we do in a lot of different inductive proofs because it doesn't hold for 1. 1 factorial is equal to 1, and then 2 to the 1st power is equal to 2, and 1 is not greater than 2. It also doesn't work for 2, and it also doesn't work for 3. You can verify those yourself. But that's why we start with 4 in this case. Now, the next step in an inductive proof is going to be writing the inductive hypothesis. So we say, assume the statement holds. The statement is P of k or P of n. You say, assume P of k holds for some k greater than or equal to 4. Consider pk plus 1. So our hypothesis is that we say that k factorial is greater than 2 to the k for some k that we choose that's greater than or equal to 4. And then we want to consider our next term. We want to show that under the assumption that p of k holds, that p of k plus 1 holds. So to do this, we're going to do the inductive step. And to do these inductive proofs where you have an inequality, it's often helpful to start off with one of the sides of the inequality. In this case, I'm going to be starting off with the factorial side of the inequality. So I'm going to write down k plus 1 factorial. And remember, our goal is to show that this is greater than 2k plus 1. If we can show this under the assumption that p of k holds, then it shows that it holds for all natural numbers greater than or equal to 4. So the first step that we're going to take, we're going to do a little bit of algebraic manipulation, and we're going to use the fact that k plus 1 factorial is equal to k factorial times k plus 1. If this isn't immediately obvious, don't worry. It's pretty standard. If we just choose, say, our number as 4, then 4 factorial is equal to 4 times 3 times 2 times 1. But 3 times 2 times 1 is equal to 3 factorial. So 4 factorial is equal to 4 times 3 factorial. So we just generalize this fact and we use it for k plus 1. That's exactly what we have here. And it can kind of give a hint as to what's going to go on later. Since we know that the statement holds for the k, if we can break it down to where we obtain this k factorial term, it becomes easier to build these inequalities. And that's exactly where we use the inductive hypothesis. Since we know that k factorial is greater than 2 to the k for this k, we can write that this is greater than 2 to the k times k plus 1. Because we know that k factorial is greater than 2 to the k, it's what we've assumed, if we just multiply both sides by k plus 1, the inequality stays the same. Now, the next step that we can take is that we'll notice that since we're starting at 4, take 4 plus 1, plug in 4 as your k. Then even at the smallest term that we're starting with, 4 plus 1 is equal to 5, which is going to be greater than 2. So we can write that this is greater than 2 to the k times 2. And of course, as k increases, this is still going to hold. But 2 to the k times 2 is equal to 2k plus 1. And this is exactly what we wanted to show. We have shown that k plus 1 factorial is greater than 2 to the k plus 1. So by induction, p of n holds for all n greater than or equal to 4. And how this works is when we assume that it holds for some k, we have now shown that under that assumption, the next term will always hold. So we start our base case where we take 4. And since we have now proven that every time that the statement holds for some number, that the next number will hold, we know that P of 5 must hold. And now since P of 5 holds, we have also proven that P of 5 implies that P of 6 must hold. And this means that P of 6 implies that P of 7 must hold. And that's why it works for all natural numbers greater than or equal to 4, because you can just keep doing this. And that's the domino effect that many people might reference when they're trying to explain how induction works. Overall, I hope that this was helpful, and thank you for watching.